Welcome to the deep dive.
Yeah.
Today we are pulling back the curtain on something many of you probably interact with constantly if you're working with Ruby.
Mm-hmm.
The build system of CRuby. The main official implementation of the Ruby programming language.
Right.
We're taking a really deep dive into a presentation by Yuta Saito, which lays out the history, the current state, and, well, the future direction of how Ruby actually gets built from source code.
Yeah, it's a great source for this.
Our mission today is really to understand that process, its surprising complexity, the unique challenges the maintainers grapple with, and maybe where things are headed.
Exactly.
And why does this matter to you listening? Well, even if you just type urbanv install or rvm install, you are relying on this fundamental process working correctly under the hood.
Absolutely. It's the bedrock, really.
It's the bedrock your Ruby environment is built on. So let's dig in.
That's right. I mean, most users, they get Ruby through those fantastic version managers like urbanv or rvm.
Man, make it so easy.
They do. They handle everything beautifully for you, but they are, well, essentially automating a core set of steps, going from source code to a runnable Ruby executable.
Okay, so what are those core steps then? What actually happens when you hit go on one of those installations?
At its most basic, for anyone building on a Unix-like system, it's usually 3 main commands. You start with the source code, often from a tarball.
Right.
You run a script called configure, then you run make, and finally make install.
Configure, make install.
Okay. The configure script's job is basically to examine your system, like what libraries you have, what compiler features are available, and just get everything ready for the build.
Okay. Checks the environment.
Mm-hmm. Then does the heavy lifting, compiling all the source code, linking it together.
And make install.
Make install just copies the final executable and libraries into place where they need to go. Simple as that, usually.
Okay.
Now, on Windows, it's a bit different. A different flavor, you might say, typically involving configure.bat and nmake instead of make.
Got it. So that's the standard path maybe for installing a release version.
Mm-hmm.
But what if you're digging into the Ruby source itself, maybe contributing, building directly from the Git repository must be a bit different, right?
It is, yeah. There are 2 main differences when you're building from the Git source. First, you typically need a working Ruby already installed on your system.
Yeah.
We often call this the base Ruby.
Base Ruby.
And second, the main configure script, the one we just talked about, it isn't actually stored directly in the Git repo.
Oh.
You need to run another command first, autogen, to generate that configure script. It makes it from a template file, Configure.ac, using tools like AutoTools.
Ah, okay. So the Git source needs this pre-existing base Ruby to generate some files, but the tarball doesn't. How does the tarball manage without that?
Yeah, this is a really key point the source highlights. It addresses what's known as the bootstrap problem.
Bootstrap problem.
Yeah, how do you build Ruby if the build process itself requires Ruby to do certain tasks?
Right, chicken and egg.
Exactly. So a release tarball is designed to be entirely self-contained. It can't assume you have any Ruby installed at all.
Makes sense.
So files that would normally be generated during the Git build using that base Ruby things like C code for the parser or precompiled internal data structures, urbinc, and so on.
Okay.
Those are already pre-generated and just included directly in the tarball.
Ah, clever.
Yeah, it lets you start the build process without needing that initial Ruby dependency.
That makes sense. It sounds simple enough in theory, configure, make, install.
Mm-hmm.
But the source goes into quite a bit of detail about just how intricate this whole process has become. How do they even figure out what's actually going on under the hood?
Right, it's not so simple anymore. That's where the tracemake tool comes in. It's actually a custom tool developed specifically for analyzing the Ruby build.
Tracemake, okay.
It records every single command executed during the make process, along with detailed timing information for each one. And then you can visualize all this data in something like the Chrome Trace Viewer. It gives you this timeline of everything that happens.
Like X-ray vision into the build process.
Exactly like that. When you look at a trace, the build clearly breaks down into 3 major phases.
Okay.
First, there's the configure phase, which runs as basically one single, often lengthy, shell script.
Right, the setup.
Then comes the make phase, which is usually a flurry of activity, potentially parallel tasks like compiling all the C source files.
Actual building.
Mm-hmm. And finally, the install phase is relatively quick. It's mostly just copying the finished files into place.
Looking at those traces and, historical data must show some interesting trends in build time over the years, I imagine.
It absolutely does, yeah. One of the clearest trends the source shows is the the increasing time it takes just to run that configure script as Ruby versions advance?
Just Configure's getting slower. Why?
Well, the primary reason seems to be the ever-growing number of feature detection checks it has to perform.
Ah,
I mean, every time Ruby wants to support a new platform or use a new feature from some library it links against, or maybe take advantage of a modern compiler capability,
right.
a check has to be added to see if your specific system actually supports it. And critically, under the current AutoTool system, these checks run one after another, sequentially.
Sequentially. Okay, yeah, I can see how that would add up over many releases if they keep adding checks.
Yeah.
Does the size of the configuration script itself reflect this?
Oh, definitely. There's a very strong correlation. The Configure.ac file, that's the template where these checks are defined, has grown significantly. The source mentioned it's now approaching like 6,000 lines.
6,000 lines, wow.
Yeah, and the growth in lines of code pretty much mirrors the growth in configure time. More code means more checks, means more sequential work.
That complexity sounds pretty challenging to maintain. The source had a really striking point about who actually contributes to that file, didn't it?
It did. What's really fascinating there is the commit data for configure.ac. It shows one person, Nobu,
Nobu, right.
has contributed about 5 times more commits to this specific file than the next most active person.
5 times.
Yeah. It really highlights the immense effort required to maintain this complex, critical part of the build. But, it also kind of points to a potential risk if the knowledge and effort are so concentrated in one person.
Yeah, a key person dependency.
Exactly. It really underscores the need to think about maintainability going forward, I think.
So the configure step is clearly a bottleneck, or getting slower. What about the make phase itself, the actual compilation and linking? Is that growing too?
Well, yeah, the make phase also naturally takes longer in newer versions. I mean, there's simply more code and more components to build as Ruby evolves.
Makes sense.
The source contrasted some early Ruby builds, which apparently could finish in under 10 seconds,
Wow.
with modern ones like Ruby 3.3 plus neb, which can take over 5 minutes. Now, they did note the trace analysis was done with make Nash J1, so single-threaded.
Oh, okay. Slower than usual then.
Right, slower than how most users would build on a multi-core machine, but the relative growth trend is still pretty clear.
Okay, let's unpack this make step then.
Hmm.
Once configure finishes, what happens inside make? It sounds like it's probably not just a straightforward process of compiling C files one by one.
It's definitely not just a simple batch compilation, no. A major source of complexity, surprisingly perhaps, is the requirement to support a really wide range of make implementations.
Different versions of make itself.
Yeah. While GNU Make is common today, the build system also needs to work with older versions, like GNU Make 3.81, which was the default on older Mac OS versions for a long time,
Oh, right.
and also BSD Make, and of course, NMake on Windows. Each of these tools has slightly different syntax, different capabilities, and the build system has to somehow accommodate all of them.
Right, different dialects of make. That sounds tricky. How do they manage that?
Well, after configure runs on Unix-like systems, like AutoTools stuff, AutoConf, AutoHeader tools process that configure.ac file using M4, which is a macro processor. They generate the main make file.
Okay.
On Windows, configure.bat handles this part. This step also generates that crucial header file, config.h, which contains the results of all those system checks.
Right, tells the C code what features are available.
Exactly. And it also generates 2 other important files related to structuring the build rules, common.mk and uncommon.mk.
Common.mk and uncommon.mk. That sounds like they're playing some tricks to handle the differences between the makes.
They are, yeah. The source describes it as an ingenious, albeit maybe slightly tricky approach. They have a file called common.mk in the source tree that's written using syntax that NMake on Windows understands.
Okay, specifically for nmake.
Right. But for other make implementations like GNU Make or BSD Make, this common.mk file is actually pre-processed. It gets filtered, basically to generate a new file called uncommon.mk. And this filtering strips out all the NMake specific parts.
Ah, okay, so they generate a specific version for non-nmake builds. Here's where it gets really interesting, maybe. So how do the main make files actually pull all these pieces together depending on which make tool you happen to be using?
Yeah, this is where the structure gets pretty complex. The way the main make file includes or uses these other files varies quite significantly based on the make tool detected.
Okay.
So for GNU-make, the main make file includes a base set of rules, plus that uncommon.mk file we just talked about, the one generated for non-make builds, and also a file with some GNU-make specific rules.
Got it. 3 parts for G and U make.
Right. But for nmake on Windows, the structure is totally different. The main make file includes a different set of submake files, and it includes the original common.mk as is without the filtering.
Completely different includes.
Yeah. And then for other makes, like DSD make, it's different again. The configure script itself actually just concatenates common.mk and the base rules file into a single big make file instead of relying on makes include mechanism at all.
Wow.
It's quite a dynamic setup just to get the right set of build rules loaded depending on your specific system and the make tool you have installed.
Wow, that's a lot of conditional logic just to get the build started.
hmm
Once the make files are finally set up correctly, what's the actual sequence of events when make runs? What gets built first?
So the build process itself happens in stages. First, it compiles the core of the interpreter, the main C files that make up the heart of Ruby.
The essentials.
Right. Once that's done, it builds something called mini Ruby.
Mini Ruby.
Yeah. It's a minimal, kind of temporary Ruby executable. It's just capable enough to run some basic Ruby scripts that are needed later in the build process itself.
Okay, a helper Ruby.
Then it uses this newly built mini Ruby to configure and compile all the standard extension libraries that come with Ruby.
Ah, uses Ruby to build Ruby extensions.
Exactly. And finally, all the compiled pieces, the core interpreter, and all the compiled extensions are linked together to produce the final Ruby executable that you'll actually use.
Mini Ruby. So there are multiple Ruby executables involved in building Ruby itself. We talked about base Ruby for Git builds earlier.
Correct. Yeah, the build process actually uses a few different Ruby variations, each for a specific purpose. The base Ruby, the one you might already have installed,
Right.
that's used early on, but only when building from Git source. It's for tasks that require running some Ruby code just to generate build files or code needed later.
And Mini Ruby, what's the specific job of that executable?
So mini Ruby is built next, and its main job is to handle configuring the extension libraries. It's used to run the system called mkamf, which relies on extconv.rb scripts found within each extension's directory.
Okay, the extension configuration scripts.
Right, those extconf.rb scripts, they need a working Ruby interpreter to run and figure out how to build the extension on your system.
Right.
But you can't use the final Ruby yet because, well, it's not fully built.
Right.
And for tarballs, you can't assume a base Ruby exists. So mini Ruby kind of fills that gap. It's the interpreter available at that specific stage.
Makes sense.
Although the source note's an interesting exception when you're cross-compiling.
Building for a different architecture.
Exactly. Building Ruby for, say, ARM while on an x86 machine. In that case, the base Ruby is used for this extension configuration step instead of the target mini Ruby.
Why that?
Because the mini Ruby that was just built is for the target architecture, ARM in the example, so it wouldn't actually be executable on the build machine x86. The base Ruby, running on x86, has to run the configuration scripts instead.
Ah, okay, that detail makes sense. And the compilation of those extensions, the source described that as literally a recursive make. What does that mean exactly?
It means that after the core interpreter is compiled, the main makefile kicks off a process for the extensions. First, it runs make with specific targets, like Configure.ac, which uses mini Ruby or base Ruby for cross-compiles, to configure each extension one by one.
Okay, configure first.
Then it runs make again with another target, maybe called xmake. And this xmake target is responsible for compiling the extensions. But crucially, the way it does this is by itself running make, again, recursively, within each individual extension directory.
So make calls make, which calls make.
Exactly. It descends into each extension subdirectory, runs make there to compile its C code into an object file, and then eventually all those object files are linked back into the main interpreter binary. So it is indeed a layered, quite literally recursive process.
Wow, okay. So we really peeled back the layers here. From a simple user command like urbanv install down through configure and make, revealing these stages, conditional make files for different tools, generated files, multiple temporary Ruby executables like mini Ruby, and even recursive steps for building extensions. This system, clearly built up over decades, must face some pretty significant challenges. with all that inherent complexity.
It absolutely, yeah. The source outlines the main problems pretty clearly. The first one is just the sheer number of build variations they have to support.
Variation.
Think about it, different operating systems, right? Unix likes, Windows, different build configurations like building inside the source directory versus building in a separate directory, dynamic linking versus static linking, and as we saw, whether a base Ruby is available or not.
It's a lot of combinations.
It is, and the difficulty isn't just having these variations, but that the logic to handle all these different combinations is kind of scattered across many different files. It's in Configure.ac, it's in the make files, it's in various helper scripts. It makes it really hard to get a global handle on how a specific combination actually behaves.
Yeah, handling all those possibilities spread out like that must be a nightmare to maintain, and especially to debug if something goes wrong.
It can be, definitely. And that ties directly into the second challenge, which the source calls make-time dynamism.
Make-time dynamism.
Yeah. The build system uses some really powerful features within Make itself, but these can be very hard to understand and debug just by reading the code.
Like what?
For example, they use patterns where make targets are named things like target yes or target no, and the actual target that gets run depends on variables set much earlier, maybe in the configure script. It makes it incredibly difficult to just look at the make file and know for sure what commands are going to execute without actually running the build and tracing it.
Right. The logic isn't obvious from the structure.
Exactly. And the source suggests this difficulty stems partly from the limited expressiveness of Configure.ac, the AutoTools input file. Because it's hard to express complex conditional logic there, more of that logic gets pushed down into the make files themselves using these powerful but often opaque make features.
You mentioned the bootstrap problem earlier, and how a tarballs shouldn't need a base Ruby.
Yeah.
Is ensuring that dependency doesn't accidentally sneak back in a challenge?
Yes, that's a significant one. Preventing unintended base Ruby dependencies in tarball builds. By design, as we said, tarballs shouldn't need a base Ruby at all.
Right.
But because the system is so complex and has evolved over time, sometimes a part of the build that shouldn't need Ruby accidentally tries to use it. And if a base Ruby just happens to be present on the user system,
It might work accidentally.
it might succeed, yeah, but behave slightly differently than intended. Or it might fail unpredictably on a system that doesn't have a base Ruby. It's apparently hard to automatically verify that a tarball build is truly free of these dependencies, and the source notes it has caused real tricky problems in the past.
Subtle bugs. And finally, performance. We saw the build times are increasing. Is that just inevitable, or is it a challenge inherent in the system's current design?
Well, it definitely contributes. Build time performance is a clear challenge identified in the source. We already talked about the configure script being a single sequential process.
Right, all those checks, one by one.
Exactly. All those feature checks can't run in parallel within the current AutoTools framework. But the make phase also suffers from performance issues due to what they call stage-wise dependencies.
Stage-wise dependencies.
Remember how we said all extensions are configured before any of them can start compiling? Looking at the build traces, like the ones from TraceMake, shows these periods of idle time. You see literal white space or blue hatched areas, as the source described them, where processor cores are just sitting idle, waiting, because the dependencies from previous stages, like all the configuring, haven't been fully met yet.
So the work isn't spread out efficiently.
Pretty much. The system isn't currently set up to build a global view of the entire build graph, which would allow it to optimize the scheduling across all tasks, including configuration checks and compilation steps, to minimize that idle time.
So, okay, what does this all mean? We've got this system that got complex over time, understandably, to handle all the requirements. But now it faces these major challenges around its scattered complexity, this hard-to-debug dynamism, potential hidden dependencies creeping in, and performance bottlenecks.
Yeah.
What's the vision for tackling these issues? Where do they go from here?
The source presents a pretty clear vision for a new direction, actually. The core idea is to move the build logic away from the less expressive tools like Make, Embo, and M4, which AutoTools uses, and actually write it in Ruby itself.
Use Ruby to define how to build Ruby. Makes sense.
It does, right. Using Ruby means you're working with a real programming language. It offers much better expressivity, clarity, and better tools for defining complex logic compared to, makefile syntax or arcane M4 macros.
Moving the logic to Ruby makes intuitive sense, especially for Ruby developers themselves. How else does this new approach aim to address those challenges we talked about?
Well, by having the build process defined in a structured way in Ruby, the system can be designed to analyze and, importantly, validate the entire build plan before it even starts executing any commands.
Validate beforehand.
Yeah. This is key for catching those potential unintended dependencies, like the base Ruby one, much earlier in the process.
Ah, okay. Proactive checks.
Exactly. And for performance, the vision includes integrating feature detection directly into this new Ruby-based system that could potentially allow for parallelizing those system checks, which are currently sequential in Configure.
Parallel checks. Nice.
And crucially, it aims to build a single, comprehensive build graph for the entire process, moving away from that recursive make structure we discussed.
A single graph.
Right. This allows for global optimization of task scheduling. You can see all the dependencies at once and figure out the best order to run things, potentially reducing that idle time significantly and improving parallel execution.
This sounds like a pretty significant undertaking. The source mentioned there's actual work underway on this new build system, right?
Yes, absolutely. There's an ongoing project to build this new system based on that vision. It has three key points, really.
Okay.
One, defining the entire build graph using Ruby for that clarity and expressivity. Two, making the build system itself available as a Ruby library. And three, importantly, ensuring that despite being written in Ruby, the end user does not need Ruby installed to build Ruby itself from a source tarball.
Wait, hold on. The build system is written in Ruby, but the user doesn't need Ruby installed to run it. How does that magic happen? That sounds contradictory.
Yeah, it sounds a bit weird, but this is a crucial design choice to maintain the familiar CRuby distribution model. Unlike some other modern build systems like maybe CMake or Mason.
Right, where you need CMake or Meson installed first.
Exactly. They generate make files or Ninja files, but you need their executable to do the generation. This new Ruby system takes a different approach. It converts the Ruby-based build description into a traditional auto tools like Configure script and generated make files that can be distributed within the tarball.
Ah, so the Ruby code generates the old style configure and make file.
Precisely. So the end user still gets that familiar configure, then make install experience, which, as we established, doesn't require a pre-existing Ruby installation if you start from the tarball.
Clever. So the generated artifacts, the configure script, and make files, they might not be as easily understandable or analyzable as the original Ruby description,
Probably not, no.
but they provide that necessary compatibility for distribution and bootstrapping.
Exactly. It keeps the user experience consistent.
Okay, that makes sense now. And the second point, making the build system itself a library. What's the benefit there?
Making the build system available as a Ruby library is actually a really powerful idea. It allows for programmatic interaction with the build graph definition,
Meaning?
meaning you could potentially write Ruby scripts to analyze the build dependencies automatically or check configurations or even manipulate the build process programmatically if needed.
For tooling and analysis.
Right. This makes it much easier to verify properties, like ensuring there are no unintended base Ruby dependencies in the tarball build plan. And it could potentially integrate better with other related tools or projects like, say, the Ruby build process for Windows, or maybe tools used by binary packagers.
It really sounds like it's directly targeting the core issues, identify the complexity, the dependencies, the performance.
That's absolutely the goal. I mean, it's still in development, as the source mentioned. Things like better documentation, full Windows support, and handling tricky dependencies that only become known very late in the build. Those are still works in progress.
Sure, it's a big project.
But the fundamental approach, moving to an expressive language like Ruby, validating the plan upfront, building a unified graph, and optimizing execution, it's really designed to solve those deep-seated problems of scattered complexity, hidden dependencies, and performance bottlenecks that are inherent in the current historically grown system. The immediate focus, they said, is just getting it capable of building CRuby itself reliably first.
This has been a really fascinating deep dive, seriously, into the intricate plumbing that actually makes Ruby work day to day. We went from the simple commands most of us use, like dev install, unpack the layers of the configure make process, saw the, well, ingenious but also incredibly complex ways it handles all those variations and dependencies.
Yeah, the common.mk, uncommon.mk trick was something else.
Right. And we examined the challenges that become visible when you actually analyze the build traces, and then got a glimpse of this future vision, aiming to make the whole process more maintainable and performant by, well, using Ruby itself.
It really does highlight the the hidden complexity that's often required to make something appear simple and just work consistently across so many different environments, that seamless experience you get with GramV or RVM, it's built on top of this incredibly layered and evolved system.
Absolutely. What stands out most to you from this deep dive? Thinking back, for me, it's probably that detail about needing to support, like ancient versions of Make, and the clever, slightly terrifying ways they have to work around those limitations.
Yeah, that's a good one. I think for me, it raises a more fundamental question, maybe,
Yeah.
about how software projects, especially really core infrastructure like a language implementation, have to constantly balance that historical compatibility and maintaining a simple user experience against the ever increasing complexity and maintenance burden of the underlying build system that supports it all.
That's a great point to leave us with. That tension between simplicity for the user and complexity for the maintainer. So maybe the next time you install Ruby, or even think about compiling it yourself, you'll have a new appreciation for the journey that source code takes to become a running executable and all the clever, sometimes complex engineering that makes it possible.
And perhaps you'll think about that deep, deep rabbit hole of bootstrapping and dependencies that lies beneath so much of the software we rely on every day. It's often more complicated than we imagine.